Okay, chapter 3, section 4. This is going to be measures of position and outliers. So in this section, we're going to cover z-scores. We're going to define what that is. We're going to look at the formula, interpret it. This is a pretty big deal in statistics. We're going to think about percentiles, again, describe what that is and how to calculate them. Then we're going to determine and interpret quartiles. We're going to determine and interpret interquartile range. And then we're going to check the data for outliers. Okay, so before or as a way to introduce z-scores, let's think about the following thing. Let me go off to the side here. Let's say that I took an IQ test. I want to see how smart I am. IQ test. The ABC IQ test. All right, so I took this test, and a week later I got my results. I scored a 4. Exciting, right? I got a 4, right? What does that mean? Is that good? Is that bad? Didn't sound very good. A 4. What does that mean, right? So in of it itself, it's just nonsense. It's just a silly value. There's no real way to determine if that's good or bad. We need more information. By itself, the score by itself doesn't really tell me anything. So if we had a little bit more information, like I gave you this, and then maybe I also gave you another piece of information, like I said, well, I scored a 4, and maybe I said something a little vague, like most people score 2. Okay, well, most people score 2, and I scored a 4, so that gives me a little bit more information. Looks like I did pretty good. Okay, I did better than most people, right? Higher than most people. Okay, but we want to be more precise in statistics. We can do better than just simply saying most people did this or most people did that. So instead of this vague statement of most people, what if I told you the median? So let's say that I have my number line. Let's put a number line on here. And then, here's 0, 2, 4, 6, 8, 10. So here's 2, 4, 6, 8, 10. And I scored this number right there. If I at least tell you the median, was equal to 6. Okay, so that would be the median is like right here. That tells me some information. Remember, the median is calculated by taking all the scores of everyone else who took this IQ test along with me, and we ordered them from the smallest score to the largest score, right? Like maybe somebody else scored a 2 and somebody else scored well, let's say there's also decimals allowed. Somebody scored a 2.1 and somebody scored a 3.7, right? And then maybe some other people, maybe there's some really smart that scored a 9. Okay, so here are all the scores. If I'm at least allowed to know that the median was 6, that means that 50% of the results are in this direction, right? It's the exact halfway mark, the demarcation of the halfway mark of the scores. Half the people who took this IQ score scored below that, and half the people scored above that. So now I have a better sense of what this means. I didn't do as well, right? I mean, half the people did better than 6, and I did worse than that. Now, just by knowing the 6 and the median, there's no indication of how many people are between 4 and 6. I mean, who knows? Maybe it turns out I was the lowest score of everyone that took it. Maybe everyone that took it was over here, right? Really kind of densely packed. Let's say that if 2 people scored the same score, let's say we put it on top to show that 3 people scored the same score there. So maybe there's like this huge clump of people over here, and here's my sad little score of 4. Maybe I'm the worst score possible, right? Just knowing that the median is 6 and I scored a 4 could be that. Or Or it could be that the other way around. Maybe there's this big clump of people way over here. Maybe most people, a lot of people scored way, way, way over here. And maybe there's nobody here. Remember, when you calculate the median, it's not true that the median has to be a value on my list. Maybe nobody actually scored a 6. Maybe from 4 it jumps to some other value over here, dot, 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 and so that when you calculate the median, it turns out to be 6, even though it might not actually be a score on our list. Okay, so having a little bit more knowledge lets me know, having a little bit more information about the median, tells me a little bit more about how to interpret this and what it means, right? Okay, another piece of information we could have is, instead of the median, we can talk about the mean. So let's erase this guy. So instead of the median, what if we know that the mean, let's put it in blue, the mean is equal to 6. Okay, so now, well, let's make it a different number. The mean is equal to 5. Let's say that information is given. Okay, well, same as before, where, well, we have a slightly, we have slightly more information than if we didn't have anything. That's a silly statement. Okay, so now, maybe instead of the median, we know the mean. Maybe the additional piece of information is the mean. So now we know that maybe like right around there is the mean, right? The average, typically in common everyday life, we think about that as the average, right? The mean. Okay, well, my score is a 4. The mean was 5. Does that mean that does that mean that I scored less than half the people? Not quite. That would be the median, right? But not so with the mean. It could be a little bit deceptive, because it could be that this is what happens. It could be that so many people scored way over here, just lots and lots of very, 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 very low scores, and then me, and then like 1 or 2 really, really bright people. And so now the mean got dragged all the way out to 5. And so a 4 is not a bad score. I could have the second highest score in the whole test, which is, not bad. But because the mean is dragged out by this outlier, right? We call these outliers. They're really far away from the norm. The outlier might be dragging the mean that way. So I'd have a skewed interpretation of my score. But still, it's better than nothing. We have more information and a better sense of how I did compared to people than if we didn't have anything at all. But still, we could do better, right? It's misleading to just focus on the median or just focus on the mean. So we want to try and do a little bit better. So let's use this technology piece over here. Okay, so here's a little simulation that can give me different distributions. So let's say, for example, I scored a 4. Let's just keep my score at a 4, and then this is everyone else and how we did. So in this kind of a situation, a 4, if this is the way things broke down, it's like the 3rd highest score, right? That's pretty good. But if we look at the mean, this is where the mean would be. Okay, so if I told you the mean was 3.03 and my score was a 4, okay, I know I did better than the mean, but it still doesn't quite capture how well I did, right? Just simply saying I scored a 4 and the mean was 3. It's not as impressive as saying I was the 3rd highest score of everyone that took this. That sounds better, and it's a better, not only is it better bragging rights, but it's more informative, right? Okay, what if it was a different distribution? How about that distribution? Remember, I scored a 4, and here's everyone else. The mean is over here. So let's say that the mean of the test was 7, and I scored a 4. You're like, okay, well, you did lower than the mean, so that does capture that you didn't do so well. But it doesn't quite capture how terrible you actually did. You got the second lowest score. There's only one person that scored lower than you. And so again, we want more information. We want to do better than that. We want to capture how rare of a score my 4 is. Is it rare on the low side? Is it unusually low? Is it an outlier on the low side? Or is it unusually high in the other direction? Okay, so let's simulate again. Look in this case. Again, we're at a case where a 4 is really the third highest score. And here a 4 is kind of clumped up with everyone else. So if I said the mean was 4.68, about 4.7, and I scored a 4, that doesn't truly capture the rest of the scores and how I did in relation to the rest of the scores. Okay, so what we're going to do is think about, come up with a way of describing one individual score as it relates to the distribution of all the rest. Good. And well, there's several ways to do that, but one important way that we're going to focus on is to think about the standard deviation of our distribution. Remember from a couple sections ago, we learned about standard deviations. A standard deviation is a value, it's a characteristic of a distribution that's attempting to mimic MAD, right? M-A-D, the mean absolute difference. It is a measure of how spread out the data is. Look at this one. Okay, it's got a standard deviation of 1.975. Most of the values are pretty clumped up, but then there's a couple really far away. Let's compare that with a different kind of simulation. This one's got a standard deviation of 2.8, right? That tells me that the data is more varied, more spread out than the previous one. Look at this one. Mostly clumped up except for one score way over there. And so if I had scored a 4 in this distribution, simply saying that I was below the mean is 7.3 and I scored a 4, doesn't really capture how terrible I did, right? I did pretty bad compared to everyone else. Everyone else scored around 8, really close to 8, and I scored half that. Only one person scored below me at a 4. So we need a better way of describing that. Okay, so what we're going to do is find the standard deviation of the distribution, and then coupled with, let's look at this. So we're going to couple that along with this idea that we learned in the previous section about the empirical rule, right? The empirical rule, remember the way we interpret this, it can be hard to imagine what this is. The horizontal axes, in my little scenario, the horizontal axes would be scores, right? And the distribution is centered at the mean. And remember that the height here could be thought of as frequency, right? So the vertical axis in this direction is frequency or relative frequency. It's, frequency or relative frequency. So how often it happened, right? So in a bell-shaped distribution, this means that this score happened the most often, right? And values around it happened a lot, right? Very common, very typical scores. And then as we move away from the mean, values become less common, less common, less common, less common, so that when you have a score, way out here, it's considered very unusual. It's unlikely to, if you randomly select a score and it lands way over here, like, oh wow, that's a very unusually high value. Or this one way over here, that's a very unusually low value. Is that a good thing or a bad thing? Well, it depends on what we're talking about. if we're talking about IQ scores, you would like a very large number, right? Like, yeah, that's good. That means I'm really smart compared to everyone else. If you're talking about, you know, something, something that involves lap times. Let's say I'm racing and I want to do a 100-yard dash and see how long it takes me to do a 100-yard dash. You want small numbers, right? That's impressive when you can do a 100-yard dash in a very and take very little time. Whereas if you take a very long time, that's not so hot. So whether it's good or bad just depends on the context of what you're talking about. So rather than think of it as good or bad, it's just unusually high or unusually low, and then it's up to you to decide whether that's a good thing or a bad thing. Okay, but what we can see from this distribution is if the underlying distribution has a bell shape like this, then within one standard deviation, we find about 68% of our data. Within 2 standard deviations, we found about 95% of our data, and within 3 standard deviations, we find about 97.5% of our data. What we should be getting out of this is that the farther away you are from the mean, the more multiples of the standard deviation away from the mean that you are, the more unusual those scores are, right? So finding a score that is 2, right, whatever that is, the mean plus 2 multiples of the standard deviation. Right? That's what this little notation means. So if you're right here, you're 2 multiples of the standard deviation to the right of the mean, finding a value there is pretty unusual, right? So telling you that I got I took an IQ test and my score, even if I don't tell you what the actual score is, if I simply indicate to you that my IQ score was high enough to be right there, 2 standard deviations to the right of the mean. I scored 2 standard deviations to the right of the mean. Isn't that exciting? Well, that does tell you a lot of information. It actually tells you more than simply telling you the actual score, right? If I told you I scored a 4, like, what does that mean? Is that good? Is that bad? Who cares? But if I told you, in addition to that, or even in replacement of, that my score was 2 standard deviations to the right of the mean, well, that lets you know a lot. That lets you know that, well, if the scores followed a Bell distribution, that would mean that I scored better than 95 plus the 2.35, about 96.7% of the population. Good. So this little tail over here is about 2.5% of the data is that way, which means that in this direction is the rest of it, which would be 97.5. So about 97.5, roughly, very, very roughly, is to the left of that. So if I told you I scored 2 standard deviations to the right of the mean, that means that I did better than 97.5% of the other applicants that took this IQ test. That's very good, right? On the other hand, if I told you, you know what, I scored 1 standard deviation below the mean, right? That would be this one. Whatever the mean is, whatever the standard deviation of the distribution is, you subtract them. You subtract the mean minus 1 multiple of the standard deviation, and you get to this score. Let's say that was my score. That's a 4. A 4 is right there. How does that compare to everything? Well, okay, again, this thing separates it. To the left, we have about 2.54, about 16% of the data is to the left of that score, right? That's going to be about 2.5, makes it about 16, which means that about 84% of the data is that way. So that's not that great. Whatever my score is, okay, I scored a 4, and that's equivalent to a value that is 1 standard deviation below the mean. Well, that's not so hot. I'm saying that about 84% of the applicants, of the other people that took this IQ score, scored better than me. Okay, so that's not a great score. Okay, so that's the mechanism we're going to develop. We're going to talk about the multiples of standard deviations. If you're minus 1 standard deviation, if you're above 2 standard deviations. Now, it doesn't have to be a whole number. I've just been focusing on whole numbers because that's an easy place to start. But rather than saying a whole number, it could be that my score was a value, I don't know, somewhere in there. Maybe 4 lands in there. You know how messy life is. Rarely do we have nice, pretty whole numbers. So maybe I need to figure out how many multiples of the standard deviation below the mean is a 4. And that could be a decimal, like it could be half a standard deviation below the mean. It could be 0.3 multiples of the standard deviation below the mean, right? So we want to figure that out. How do we do that? Okay, well, first of all, we need to figure out what the mean is, so that to calculate that value. So we're going to have to find this distance. That'll be that distance there. And then we need to figure out how many multiples of the standard deviation is that. So we need to divide it by the standard deviation of the distribution. Okay, well, exactly that is the topic of this section. That's called the z-score. The z-score is exactly what we just described. It's a number that represents how many multiples of the standard deviation to the right or to the left of the mean is a unique value, right? So every unique value, every value in your set will have its own z-score, right? Because it depends on where it is in the distribution. Good. So the z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data and dividing this result by the standard deviation. There is both a population z-score and a sample z-score. Okay, well, the only difference between the two formulas is, of course, that if we're dealing with a population, then mu is the mean of a population and sigma is the standard deviation of the population. Whereas if it's a sample, then this is the x bar is the mean of our sample, and s is the standard deviation of our sample, right? Standard deviation. This is the mean of our sample. Here, if this was a population, then this is the mean, and this is the notation we use for standard deviations. This idea of how many multiples of something I think is hard for people to grasp, but remember that we do that already all the time. If I think about my height, somebody asks me how tall am I, and I go, okay, well, I'm 5 foot 9 inches. 5 foot 9 inches. We're really comfortable with that because we already know how tall that is, right? We can visualize it. We know approximately how tall is someone that's 5 foot 9 inches. But what is a foot? Who said that that's a foot, right? What is an inch? Who determined that's an inch, right? And in fact, with the English system, all our units of measurements are kind of funky things, right? You should look those up. They're kind of fun. Who decided what an inch is, right? They went to the king and they measured his thumb. Like, okay, here's his thumb. Like, we'll call that an inch. They have weird ideas of what it is. But we can easily use other things. If you tell me how tall am I, and I told you I'm 17 calculators tall, right? If you stand these calculators end to end and end from the floor up, I'm 17 calculators tall. I could say that, right? In multiples of calculators, how tall are you? I'm 17 calculators tall. Well, let's be more precise, right? What calculator? I'm 17 TI-84s tall. TI-84 tall. Good. Like, okay, well that's a number, but we're just not used to that, right? We're not comfortable with that because we're not used to seeing that. Um, or how tall am I? I'm, what would it be? Maybe like one 180 187th of a football field. Well, that's, I don't know. That's probably 1/100th of an 87th of a football field. Again, that's something we're not used to, but okay, think about how big a football field is. Chop it into 187 equal pieces, and I'm one of those. That's how tall I am. Okay, again, it's not wrong, it's just unusual, right? We're just not used to it yet. So, when we're trying to think about a distance, a score, rather than just give me the score value, I scored a 4. We have this IQ test, and here is sort of a number line that has all the values of the IQ test. If I scored a 4, what we want to do is think about where the mean is. Okay, so the mean was over here. Let's say that this is the mean. The mean equaled 7. And the standard deviation of the population was, it doesn't have to be a whole number. It could be something like 3.2. Well, okay, that's fine. 3.2. All right, well, what I want to do is think about how far away below the mean this is. And then once I get that distance, okay, well, that's just 3 units. That's easy. 3 units. We're going to keep the sign. We're not going to automatically ignore it because we want to be able to identify that it's below. So the plus and minus is going to have significance here. Minus means that below the mean. Plus means you're above the mean, right? So I want to identify this as -3 units this way. Okay, well, -3 units. But that's not enough information to just say -3 units because it's important to know where the rest of the values are. If the rest of the values are this way, remember we could have a case where there's a lot of values way over here, and then there's like just one person over there, so they're dragging the mean over there, right? So there's a certain amount of variability there. Or it could be the case where maybe all the other values are really clumped up around that mean, right? And so now having a score of 4 is pretty bad, right? So we need to incorporate what the other values were doing. And to do that, we think about the standard deviation, and we want to transform this into multiples of standard deviation. So if I'm told that the standard deviation is 3.2, then that means that this distance over here, this -3 units, is a little bit less than 1 standard deviation. Okay, and that's what the z-score is going to be. So let's look at our formula, or let me write down the formula one more time. The z-score is equal to the x value minus the mean divided by the standard deviation. Standard deviation. So if we're talking about populations, in a population, the z-score is equal to x minus mu, because it's a population, divided by sigma. So in this case, that means that my z-score for the value 4 is equal to 4 minus 7. That'll give me that -3 divided by 3.2. And so that'll be 3 divided by 3.2. And 3 divided by 3.2 is 0.9375. 0.9375. Right? So what does that mean? It means that this means that the value 4 is 0.9. Oops, sorry. This is -3. This is minus 3, which means that this is negative, right? Negative is important. So this means that, so the score of 4 is 0.9375 multiples of the standard deviation below the mean. Below the mean. Right? Below because it's negative. In this context, that means that that's not so hot, right? That's not so great. Because we would like high score values, but in other kinds of word problems, other situations, maybe you want a low score. So it depends on the context that you're doing. Okay. Not only is it good to figure out the z-score for one value so that you can compare it in relation to other scores to get a better sense of how you actually did, right? So z-score can help me figure out a position of relative standing relative to everyone else. How did I do? So that's really good for z-scores. But it's also very good to be able to compare it against other distributions. So what I mean by that is, what if I scored a, again, I scored a 4 in this IQ test, the ABC test. I scored a 4. And so let's say my friend took the, I don't know, my friend took the ZY test. Okay, some other test. And then he scored a 6. Okay, well, it's not fair to compare the 4 against the 6 because how did everybody else do? I mean, if you just do that, you know, my friend's going to claim, oh, I scored a 6, I'm smarter than you. And of course, I'm going to claim, well, your test was easier. That's why you scored a better number, right? So we need to know, relative to everyone else, how was a 4? If it turns out that everyone else that took this test was way over here like this, then a 4 is fantastic. I'm way, I did really well. And if it turns out that on his test, everyone else did like this, well, then a 6 is not so hot, right? Or the other way around, right? So there becomes some mixture. So rather than just comparing a 4 and a 6, what we want to do is find the z-score of the 4 relative to everyone else that took this exam. Of course, that means that we'll need to know what the mean and standard deviation was. So I'm just throwing out some numbers. Let's say that they're both good. Let's say that the mean was only a 2.5. So the mean was over here. So I did better than the mean. And the standard deviation was 0.7. Okay. On the other hand, my friend, he also did pretty good. The mean was 5. And the standard deviation sigma is equal to 0.25. Okay, so now with this new added information, let's figure out my z-score. So I know I did better than the mean, so I know I did pretty good. And so did he. My friend also did better than the mean from his distribution. But who did better, right? Which of these scores, another way to think about it is, let's try and figure out which of these scores is more rare in their own distribution. A score of 4 on my test or a score of 6 on his test. Which one is more rare? We know that both of them are to the right of the mean, so they're both going to be rare in the good direction in the context of this idea that these are both IQ tests. IQ. So in the context of an IQ test, we would expect large numbers to mean that you did well. So we both did better than the mean, but who beat who? Who's got more bragging rights? Me with a 4 in this distribution or him with the 6 in this distribution? Okay, so let's find the z-score associated to this one. Make some room over here. Erase that. Let's erase that. Okay, so the z-score associated with that 6, the z-score, is going to be equal to 4 minus the mean, 2.5, making it positive, so that automatically means I did better than the average. I scored higher than the mean, divided by 0.7. That's going to be the z-score associated with this one. That means that this is going to be equal to 1.5 divided by 0.77. So if we divide that, we get a 1.5 divided by 7. We get a 1.5 divided by 0.7. We get a 2.14. So traditionally, we like to round z-scores to 2 decimal places. So let's say that this is about a 2.14. Okay, 2.14 multiples of the standard deviation to the right of the mean. That's how we interpret that z-score. The mean is over here at 2.5. So the z-score of 2.14 can be interpreted as the score of 4 is 2.4 multiples of the standard deviation to the right of the mean. And remembering that with the normal going back to this, we know that the farther away you are from the mean in terms of multiples of standard deviations, the more rare an item is. So 2 standard deviations to the right, we established that that's about 97.5% of the data to the left, and only about 2.5% to the right. So we're pretty close to that. I did a little better than that. I scored it 2.14. So it's going to be a little bit better. Okay, but what about the other score? So now in this new distribution, a different test, lots of people took this one. And the mean is 5. So let's say the mean is over here. Just a 5. So what we want to do is figure out what this is and then divide it by its standard deviation to figure out how many multiples of the standard deviation to the right of the mean is the score of 6. So let's figure out this z-score. Z-score equals to 6 minus 5 divided by 0.25, which is equal to 1 divided by 0.25, which is equal to 4. Nice, pretty whole number. 4, that's 4 standard deviations to the right. And if you remember from the distribution, once we get to 3 standard deviations, about 97% of the data is within 3 standard deviations. And this is a score that's 4 standard deviations to the right. So the fact that this is a very, very small standard deviation indicates that the great bulk of our values are really clumped up together, really close to the mean of that distribution. So they were all really clumped up like this, and then here comes this 6. So it is really good compared to that, right? This is like genius status. Way, way better than everyone else that took it, right? Compared to everyone else that took it, a 6 is fantastic. On the other hand, this one is a little bit more spread out than that one, right? A 0.7 is a bigger value than that. Remember, the standard deviation is attempting to describe the mean absolute difference, MAD. It's a measure of how spread out the data is. So the mean is 2.5. 4 is a rare value, but it's not the most rare value. There's a couple scores over there, and there's probably a couple scores over there. So maybe something more like this. You know, just values here, values there, kind of more spread out. So 4 is high. I should be proud of that. But clearly a 6 in this distribution is amazing, right? That's 4 standard deviations to the right. This is a much better score, right, than a 4. Good? Okay, so we'd say the score of 6, so a score of 6 is 4 multiples of the standard deviation to the right of the mean, right? Okay, and remember, if we assume that scores are approximately bell-shaped, then we know that that is a very, very unusual score, right? If we assume that that IQ scores kind of fall this sort of a bell-shaped kind of thing, then this is really, really far to the right. 4 standard deviations, very unusual. And in this case, that's a good thing. That means this person is really smart. On the other hand, in my case, the standard deviation was 0.7. It's a little bit higher. There's a little bit more variability between the values. And so if we're assuming that it's approximately bell-shaped, maybe it's something like that. It's still high up there. It's still a very, should be proud of that score. But it's not quite as dramatically great as that one. And you wonder, well, what if it's not bell-shaped? That's okay. Remember, Chebyshev tells us that for any data set or distribution, at least this amount of the observations will be within k values. So what we could see from here, what this formula tells us, is the bigger the k value, the more information that lies within it. Right? So if we have something where here is my mean, and you're like, let's go out to 2k, 2 standard deviations. So k equals to 2. That means we go out 2 standard deviations to the left and 2 standard deviations to the right, like this, of the mean. So let's say this is a sigma length, this is a sigma length, a sigma length, sigma length. 2 this way, 2 this way. That's k equals to 2. So my little formula says that according to Chebyshev, it doesn't matter what the distribution is, we will get at least 1 minus 1 over k squared. So in this case, it's going to be 2 squared. That's going to be 1/4. 1 minus 1/4, that's going to be equal to 3/4. Or at least 75% of the data, or more. So even if the distribution is not bell-shaped, a score of a z-score of 2.4, a z-score of 2.14 is still going to be really good. It's unusually, it's a little unusual, right? Most values are within 2 standard deviations, at least 75% of the data. So I'm over here. If it's symmetric, that means that the extra 25, right? If this center is 75, if it's symmetric, I'm thinking about half of it is on this side, or 12.5, and about the other half is on the other side, or about 12.5. So that would indicate that this is an unusually high value. Good. And if it was a different value, like let's say k equals to 4, so here is the mean, and then I want to go 4 standard deviations, 1, 2, 3, 4 standard deviations that way, and 1, 2, 3, 4 standard deviations this way. 1 multiple of sigma, 2, 3, 4 multiples of sigma to the left, 1, 2, 3, 4 multiples of sigmas to the right. How much data of everyone that takes this score, how many of them do we expect will be within 4 standard deviations, regardless of the distribution? What Chebyshev tells us that it's going to be at least 1 minus 1 over 4 squared. Right? This is where k equals to 4. And so that's going to be equal to 1 over 16, which is equal to 15 out of 16. Come on. 15 out of 16, which turns into 15 divided by 16, or about 93.75% of the data. Remember, Chebyshev says at least this much or more is going to be within 4 standard deviations of the mean. So the bigger the k value, right, looking at our formula, the bigger the k value, the closer we get to 100%, right? We're taking something away from the 1. When k gets larger, then this becomes smaller, so we're getting closer and closer to 100. So the bigger the k value, the more data is within k multiples of the mean. So we can get a really good sense that the bigger the z-score, the more unusual it is, the more rare of an item, the more rare of a score it is in relation to the rest of the values in that distribution. All right, let's try this example now. The mean height of males 20 years or older is 69.1 inches, with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches, with a standard deviation of 2.7 inches. Data is based on information obtained from the National Health and Examination Survey. Who is relatively taller? Kevin Garnett, whose height is 83 inches, or Candace Parker, whose height is 76 inches? Who is more unusually tall relative to their own distribution? So we have men and we have women, we have different distributions. For heights of people, we can assume that the heights of people are approximately bell-shaped. So we have men that are, let's make it in blue. Men, let's say that this is the distribution for men. And we have a mean, mu, equal to 69.1, and we have a sigma equal to 2.8. On the other hand, we also have a distribution for women. And for women, let's say that this distribution is also approximately bell-shaped. And we have a mean value for women. Mean value for women is 63.7. And a standard deviation of 2.7. Okay, so remember that the horizontal axi in these cases represents the heights, right? So various heights, and then the picture above is there to indicate for you which results are more likely. There was a lot more people that, a lot more men whose heights are around this in terms of inches, right? 69.1 inches. There's a lot less men that are over here because the picture above it is not as tall, it's not as high, okay? And then likewise over here, there's a lot less men that are way over here. So we got Garnett way over here. Let's just say 83 is over here, and that's unusually high. It's pretty high up there. How unusual is it, right? And we got Parker, that's way over here at 76. So which one is more unusual? 83 in this distribution or 76 in this distribution, right? So clearly we want to find the z-scores associated with each one of these in order to be able to answer this question. So let's go ahead and do that. So the z-score z-score related to the 83 is going to be 83 minus the mean, which is 69.1, divided by 2.8. So if I go over to my calculator and type that in, get 83 minus 69.1 divided by 2.8. I'm getting a z-score of 4.9696, rounding to 2 decimal places. That is very unusual, right? Way far to the right. It's almost 5 multiples of the standard deviation to the right of the mean. That's very, very unusual, very, very high. Okay, so what about the z-score associated with a 76? This z-score is going to be equal to 76 minus 63.7 divided by 2.7. All right, that would be 76 minus 63.7 divided by 2.7, which is about a 4.555, so we can say about a 4.56. 4.56. Okay, very, very high, right? It's a little bit more than 4.5 multiples of the standard deviation to the right, whereas Garnett, right, so this is women, females, whereas Garnett is almost 5 standard deviations to the right of the mean. Parker is a little bit more than 4.5 multiples of standard deviation to the right. So we can say that Garnett is the more unusual case. It's more rare to find an 83-inch tall male than it is to find a 76-inch tall female. They're both very rare at very high z-scores, but this score is a little bit higher. It's a little bit farther to the right. It's a little bit more unusual than this one. So we would say that Kevin Garnett is a more rare find. Okay. So a z-score of 4.96 is more unusual. So answering this question, who is relatively taller? Kevin Garnett is relatively taller. Relatively taller. Okay, let's see how the author organized this. Okay, so same thing we did. It's our height minus the mean divided by the standard deviation. We get this. The height of Parker minus the mean divided by its standard deviation. We get this score. So Kevin Garnett's height is 4.96 standard deviations above the mean, to the right of the mean. Candace Parker is 4.56 standard deviations above the mean, to the right of the mean. Therefore, Kevin Garnett is relatively taller. Kevin Garnett's score is a little bit larger. Z-score is a little bit larger. Therefore, he's a more rare find within his own distribution. All right, let's move on to something called K percentiles. So the kth percentile, denoted by P sub k of a set of data is a value such that K% of the observations are less than or equal to that value. So it's best to imagine a very, very large data set. So let's say that I have some data set that is very, very tall. Like let's say, very large. Like let's say, for example, I asked all I asked all El Camino College students their, what do I want to ask? Mm, I asked them, well, let's stick to heights. Well, I asked I asked the El Camino College students their heights in inches. So there's going to be a lot of scores. So let's say they go all the way down from 40 inches to 50 inches to 60 inches to 70 inches to 80 inches, and so on and so forth. So there's 25,000 students, so they're going to be all over the place. Some values there, some values there, some values there, just all over the place. Right? So there's just a lot of values. What we want to do is imagine taking all of those scores and breaking them up into 100 equally spaced little cells like this, where the score right there, the height right there could represent a score such that it traps 1% of the data. 1% of the data. So therefore, that score is piece of 1. It's the first percentile. Good. The next one is also 1% of the data. So then that score right there would represent piece of 2, right? The second percentile, dot, 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 dot. We keep going. Maybe at some point over here, there's a place that captures 50% of the data. Call that P sub 50. Good. The 50th percentile. The 50th percentile. Well, we already know what the 50th percentile is. That's also equal to the median. Okay, the 50th percentile is the median. So that's what we're looking for. So when we have a very large data set, it makes sense to be able to visualize us breaking this up into 100 equal pieces, and then we're looking for the values that represent certain percentiles. Right? The kth percentile, denoted by P sub k of a set of data, is a value such that k% of the observations are less than or equal to that value. Okay, so for example, the Graduate Record Examination, GRE, is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than 70th percentile for admissions into the Human Genetics MPH or MS program. Okay, interpret this admissions requirement. Okay, so if we take, I'll just put it here. To interpret this, if we take all scores that anybody takes, GRE scores, and I'm not really sure what the scale is. Can you score a 7? Is that a possibility? Is that good? Is that bad? I'm not really sure what the scaling is, so I'm just gonna make something up, and it's probably wrong. But let's say it goes in. Let's go by hundreds. Let's go with multiples of 100. So 100 there. 2. Let's make it. So let's make it 0, 200, 400, 600, 800, 1,000, 1,200, 1400, 1600, 1800, and 2000. Let's say that the scores just go between 0 and 2000. So scoring in the 70th percentile means that if we take everybody that took this score, maybe some people scored over here, some people scored way over there, right? Based on the actual results that we see, what we want to do is figure out the value, the score that separates the lowest 70% of the scores compared to the highest 30% of the scores. Good. So we call this P sub 70. P sub 70 will be a score, right? This will be equal to some score such that 70% of everyone else, of other test takers, of other scores, are below and 30% are above. Right? It's like a knife, and you're slicing this guy and you're cutting this cake so that 70% of it is that way and 30% of it is that way. And I should have said that, not the it, but the scores. 70% of all the other scores are this way and 30% of them are that way. That doesn't give you really much indication of where they are, where the other ones are. For example, it could be that 70% of the scores are all like right here. Maybe they're all really clumped up, really close to that value, but it doesn't matter. 70% are this way and only 30% are that way. Or it could be that they're not really all clumped up. Maybe they're way over here. Maybe they're really evenly distributed. Right? But 70% of all the scores of everyone else that took this test, this score, the P sub 70 score, will be the score that separates the lowest 70% of all the scores compared to the highest 70% of the scores. Right? That's the idea we're going after, whatever that value may be. This is just an arbitrary place where I chose the P sub 70 value to be, but who knows, maybe in actuality it's way down here. Maybe most people do really poorly. 70% of the people score below 400, for example, might be a really low score. Or it might be really high. Maybe 70% of the people score way, way over here, and then only 30% of the people are really clumped up way up here in the high end. Good. So that's the interpretation of the 70th percentile. It's the value that separates the lowest 70% of the scores from the highest 70% of the scores. So in general, the 70th percentile is the score such that 70% of individuals who took the exams scored worse and 30% of the individuals scored better. In order to be admitted into this program, an applicant must score as high or higher than 70% of the people who take the GRE. Put another way, the individual score must be in the top 30%. Right? That's another way to interpret that as well. Okay. So quartiles. Quartiles divide the data set into fourths. So the median, where we break it up into the lowest 50%, 50% goes that way to the left of the median, and 50% goes that way to the right of the median. Well, another popular way to divide things up is into quarters, where we are looking for a value, which is also known as P sub 25, that distinguishes between the lowest 25% of the data and the highest, well, that would be 75% of the data. Right? The value that separates the lowest 75% of the scores in our set compared to the highest 75% of the scores in our test. Okay, and then the 75th percentile, the third quartile, would be P sub 75, and that's the value that separates the top 25% of the scores compared to the lowest 75%. A very common thing is for people to misunderstand the meaning of quartiles or percentiles. They are not referencing, so saying that the 25th percentile, the 75th percentile does not mean that you got 75% of the questions correct. That's not what that means. It doesn't mean that your score was 75%. That's not what that means, right? It's a percentage of all the other scores in your set. Good. It's the score, whatever it may be. Could be a big score, could be a little score. We don't know. It could be. It's the score that separates the lowest 75% of other scores from the top 25% of all the other scores. Okay. So the first quartile, denoted by Q1, divides the bottom 25% of the data from the top 75% of the data. The first quartile is equivalent to a 25th percentile. Good. Same thing for the second quartile. It divides the bottom 50% of the data from the top 50% of the data. Also, the second quartile is also known as the median. And then finally, the third quartile separates the bottom 75% of the data from the top 25% of the data. Okay, well then how do you find it though? So we have an idea of what the quartiles are, what the percentiles are, but how do you find them? Okay, so in order to find the percentiles, we're going to arrange the data in ascending order, right? That means from the smallest to the largest. Smallest to largest. That's what ascending means. So arrange our data from in ascending order from the smallest to the largest. We're going to determine the median, right? M. We already know how to do that. We have rules for that. Is it an even number of values? Is it an odd number of values? Remember, there were two separate rules for that. So figure out where the median is, also known as Q sub 2. We divide the data set into two halves, the observations below to the left of the median and the observations above. So then the first quartile, Q1, is the median of the bottom half, and the third quartile, Q sub 3, is the median of the top half, right? So we're going to do this kind of in steps. If we have a big set of data, right, we have a bunch of data points on my number line. They're here, they're there, they're all over the place, right? So the first thing is we're going to figure out where the median is of the whole set. Median. Well, that's going to be equal to Q sub 2, also known as P sub 50. And then we're going to focus on the values that were in the lower half, and then we're going to find the median of that, of just this, the little local median here. This little median of this little set, well, that's going to be Q sub 1, also known as P25. And then we're going to, so this bottom half, and then we're going to focus on the data that's in the top half, and we're going to find the median there using our rules for the median. So this is the median of the top half, which separates the top half into the lower 50, the top 50% of the scores. Okay, so then that is going to be equal to Q sub 3, also known as P sub 75. So this will be our strategy for finding Q1, Q2, and Q3, if we have to do it by hand. Otherwise, we'll see how we do it with our technology. Okay. A group of Brigham Young University, Idaho students, Matthew Herring, Nathan Sparren, Mark Wahlberg, and Mark Steiner. Sorry, Mark Walker, not Wahlberg. Mark Walker and Mark Steiner collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed limit is 25 miles per hour. The recorded speed of 14 randomly selected vehicles is given below. Okay, so we want to find find and interpret the quartiles of this thing. Okay, so we want Q1, Q2, Q3, and Q4. So there are 14 values. That means that n equals to 14. Remember, it's even. When it's even, to find the median, remember that the median is going to be the mean of two numbers after we place them in order from the smallest to largest. So luckily, that has already been done for us. We don't have to worry about that part. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them, and they're already from the smallest to the largest. So if we focus on, say, this number, there's 1, 2, 3, 4, 5, 6 numbers below, and 1, 2, 3, 4, 5, 6, 7 numbers above. So that can't be the number in the middle. And same thing if we switched it over here. If I thought about this one, well, then that would mean there's 1, 2, 3, 4, 5, 6, 7 numbers to the left, and 1, 2, 3, 4, 5, 6 numbers to the right. So we know that when we have an even number of entries, we are not going to get a unique, we're not going to get a member value of our list that separates the lower half from the top half in a fair way. So the rule says that the median in this case is going to be equal to the mean of scores in spot number. The 14 divided by 2 will be the first one. So 14 divided by 2, that's 7. So the 7th spot. Change this to color. 1, 2, 3, 4, 5, 6, 7. This is the 7th spot. And the one right next to it. And spot number 14 divided by 2 plus 1, in this case, will be 8. What do I do here? Sorry. This is 7. And then the one right next to it is 8. So we take these two numbers, and they have 1, 2, 3, 4, 5, 6 numbers to the left, 1, 2, 3, 4, 5, 6 numbers to the right. So the mean of those two will be our median. Median equals to 32 plus 33 divided by 2. That's going to be equal to 65 divided by 2, which will give you 32.5. Okay, so 32.5 right in the middle here. That'll be our median. Median, which is also equal to Q sub 2, which is also equal to P sub 50. It goes by all those names, the median, the second quartile, P sub 50, and in this case, it's equal to 32.5. Good. Once we have that, once we've established that the median is going to go right there, now we kind of focus on the bottom half and the top half. So these numbers here are now going to be the bottom half, including this 32 because it's to the left of the median. And then including this 33, this over here is going to be my top half. This is my top half. This is going to be my bottom half. So in the bottom half, I have 1, 2, 3, 4, 5, 6, 7 values. That means that n is odd. And that means that my rule for the median of the bottom half, median of bottom half, is going to be the value in spot value in spot number n plus 1 divided by 2. That was the little formula for it. In our case, that'll be equal to 7 plus 1 divided by 2 equals to 8 divided by 2, which equals to 4. So the rule says that the value in the fourth spot is the median of the bottom half. 1, 2, 3, 4. That's this guy. Let's put a highlight on it. That's this guy. The 28 is the median of the bottom half, which then means that this is Q1. Q sub 1. Also known as P sub 25. Also known as P sub 25, which is also known as 28. 28 is the first quartile. It's P sub 25. It's also 28. Good. Then we'd have to focus on the top half, right? So if this is my top half over here, so my top half has the has 1, 2, 3, 4, 5, 6, 7 values as well. And so we follow the same rule as before. So the median in this case is also going to be equal to the value in the fourth spot. Fourth spot. And so that would be 1, 2, 3, 4. That would be equal to the 38. Right? The 38 is the median of the top half, which then makes it the Q sub 3 value, also known as P75, also known as 38. Good. So organizing these, it's a little messy there. So Q sub 1, we discovered that Q sub 1, which is also known as P25, is equal to the 28. Q sub 2, also known as P sub 50, also known as the median of the entire thing, of the original data, median, is equal to 32.5. And finally, Q sub 3, which is also known as P sub 75, is equal to 38. All right, let's see if the author matches with my assessment of things. So we can see down here that that's how the author found the first value. There's 14 observations, so the median, or the second quartile, is the mean of the 7th and the 8th observations. Good. Following our rules for how to find medians from Chapter 3, Section 2, or Section 1, I think. One of those two. Okay. I think it was Section 1. Chapter 3, Section 1. Then, the median of the bottom half of the data first. Okay, so then now we have 20, 24, 26, 28, 29, 30, and 32. That's this set in green here. That takes care of these guys. And so now the median of it is the seventh observation, which is equal to 28. Good. Following this rule over here, with n equals to 7. And then following the same work, we get that the third quartile is going to be equal to 38. Okay, so 25% of the speeds are less than or equal to the first quartile. That's our interpretation, which is 28 miles per hour. So about 25% of our data is below 28 miles per hour. And 75% of the speeds are greater than 28 miles per hour, right? That's the separator, right? If we have car speeds, then the fact that we found 28 over here, 28 miles per hour, as the 25th percentile, it means that it is the boundary point that separates 25% of our data. 25% of all the vehicles are below 28 miles per hour, whereas 75% of the vehicles are above that speed. Good. For the median, we've worked with that before. It's the same thing. We have car speeds, recorded car speeds, then approximately 32.5 miles per hour is the median. So about half, about 50% of the scores are above that, and about half, or about 50% of the scores are below that. And then finally, if we have a value there, which was 38 miles per hour, the car speeds, then the 38 miles per hour being Q sub 3 means that it is the score that separates the top 25 scores from the bottom 75 scores. 75% of the cars that we recorded traveled at a slower speed than this, and 25% of the cars traveled at a speed higher than that. Okay, the IQR value, the interquartile range is the IQR, is the range of the middle 50% of the observations of the data. That is, the IQR is the difference between the third quartile and the first quartile. All we have to do is find the quartiles and subtract them, Q sub 3 minus Q sub 1. That's how we find the IQR. Okay. So in our little example, we found that Q sub 1 was 28 and Q sub 3 was 38. So if we subtract them, then we get that the IQR equals to 10. IQR equals 10. So the range of the middle 50% of the speeds of cars traveling through this construction zone is 10 miles per hour. The middle 50% of cars, the range of the middle 50% of cars is 10 miles per hour. So suppose a 15th car travels through the construction zone at 100 miles per hour. How does this value impact the mean, the median, the standard deviation, and the interquartile ranges? Okay, so just tossing it in there, this is what would happen. Without the 15, we found that the mean is 32.1 miles per hour. The median is 32.5 miles per hour. Standard deviation is 6.2 miles per hour, and the IQR is 10. Let's confirm that these are the results by adding that extra car by using our calculator, and this would be a good place to introduce how to do this work with your calculator, which we've already done anyway, so it's a good place to review. So let's go back to our original data. Up here. So here's the original data of our cars. And let's use our calculator to find all those results. So we're going to go over to Okay, so once you turn it on, hit clear. It's a little too big. Okay, once you turn it on, hit clear and quit to exit any unusual screen you find yourself in. We're going to go to stat. We're going to get a calculate. I'm sorry, stat, and then we're going to go into edit. It's exactly where we want to be at. If you have information from prior ones, you can erase them. So I'm going to use list 1, clear, enter. And so I'm going to input the data points right into there. So we have 20. Okay, so those are all the data points onto one list, and now we're going to do one variable stats on this list. Scoot this over a little more. There they are. Okay, so let's do stat calculate one variable stat on list 1. So hit enter, 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 calculate, and there's everything we need. We have the mean of our set of values, 32.1. If we scroll down, use this arrow, scroll down, we're going to get everything else we need. It also gives you the minimum and the maximum value, which we haven't gone to yet, but see they match. The minimum value on my list, yep, it was a 20. And the maximum value on my list, it was a 40. And then the first quartile was 28. Through the work we did before, it matched. In fact, I think I have it like right here. So let me. Earlier, when we did it by hand, we found these things. The median is 32.5. Median is 32.5. Third quartile is 38. 38, and the first quartile was 28. 28. So they match there. Good. And then in the table below, we have these results. So if we scroll up, we get 32.1 as the mean. The mean was 32.1. We already knew the median. Standard deviation is 6.2. Standard deviation is 6.175. Okay, so that rounds to 6.2. Remember that this is a sample. This isn't every single car that's on the road ever. It's just the sample of cars they found when they went out there. So definitely a sample. So we use the sample standard deviation, not the sigma. That's for a population. And then if we subtract Q sub 3 minus Q sub 1, we found that the answer was 10. The IQR is 10. Okay, so now let's confirm that if we toss in one more car that was traveling at 100 miles per hour, that all of these values, all these characteristics change this way. All right, so let's go back to our list, edit. And all I'm going to do is just come down here at the very bottom and add one more value, 100. Enter. So I have one more value, and then I'm going to go to stat, calculate, one variable statistics, enter, 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 and there we go. So now the new mean is 36.666, which rounds to 36.7. And the median, okay, use my arrows to come down here. The median is 33. Standard deviation is 18.5, so 18.5 is the standard deviation. And the IQR, well, that's going to be the difference between Q3 minus Q1. So 39 minus 28, right? Q1 is 28, Q3 is 39. The IQR value is going to be 11, right? So we can confirm that we can easily get these results with our calculator if we just add one more extra value. Okay, so what can we conclude from seeing this? we added one more value, and note that 100 is very, very large compared to the rest of the values. Right? We had scores or speeds that were in 20, 24. Remember, the speed limit was 25, I think. 27, 28, 30, 30 miles, 32, 33, so 34, 34. Right? So we had a lot of speeds, but then one person just blew everyone else out of the water. We have an unusually high number, 100. And how did that impact things? Well, it dragged everything to the right. Everything is a little bit bigger, right? The 32 went to 36, the 32.5 went to 33, the 6.2 went to 18.5, and the IQR went from 10 to 11. Okay, so remember that the mean is a little bit more sensitive to outliers, to unusually large or unusually small values. So it gets dragged toward a larger number because of the 100, right? So it gets impacted by that 100 a little bit more than the median. Notice the median also went up, but not by much, not compared to the mean. Good. The standard deviation also shot up. Remember, standard deviation is an attempt to describe MAD. It's an attempt to describe the distribution of our set. And the bigger it is, the more spread out it is along its mean, around its mean. And the smaller it is, the more clumped up the data is centered around its mean. So adding one extra value that's really far away then changes the average distance each number is away from its mean. So it increases the standard deviation up quite a bit, right? So very sensitive to outliers. Very sensitive to outliers. Not as sensitive to outliers. And look, the IQR also not as sensitive to outliers. That's good. Okay. All right, so let's move on to checking for outliers by using quartiles. So in the previous case, we tossed in that 100, and then that was a very unusually high number compared to all the other ones. It seems that that should qualify as an outlier, but how do we define it? How do we get a more precise definition of what is an outlier and what isn't an outlier? What is unusually high or unusually low? So one way to do that is to do it this way. Step one, we determine the first and the third quartiles of the data. Step two, now that we have the first quartile and the third quartile, we find the interquartile range. Right? So the first quartile, that's going to be find Q sub 1 and find Q sub 3, step 1. Step 2 is to find the IQR, interquartile range, which is equal to Q sub 3 minus Q sub 1, right? Once we find that, then we're going to do the following. We're going to find this lower fence value, and the value is Q sub 1 minus 1.5 multiples of the IQR. Whereas the upper fence is going to be Q sub 3 plus 1.5 multiples of the IQR. So it's a little mysterious as to why there's this 1.5 in here. And there really isn't a good answer that I can give you, except that that's just the standard that's been chosen. It's never going to change for us. It's always 1.5. So it's not dependent on a specific question. It's always 1.5 multiples of the standard deviation to the right of the mean, 1.5 multiples of the standard deviation, 1.5 multiples of the IQR to the left of the first quartile, 1.5 multiples of the IQR value to the right of the third quartile. That makes up our lower fence and our upper fence. What those are boundary points, such that if we find a data point in our set that is to the right of the upper fence, or a data point that's to the left of the lower fence, then we consider those to be outliers. Okay, so let's say we have our data right here, and we have Q sub 2 somewhere there, Q sub 2 somewhere there, and we have Q sub 3 somewhere over here, and we have Q sub 2 somewhere, I'm sorry, Q sub 1 somewhere over there. Well, we're going to find the IQR values, and then we're going to create these zones. So if we go 1.5 multiples of the IQR to the right of this, right, that would be the upper fence. Upper fence. That means that this distance is 1.5 times the IQR from there to there. And then we also think about this lower fence. It's going to be the lower fence, somewhere over there. Right? And so that is going to be 1.5 multiples of the IQR value to the left of Q sub 1. So that now if we look at our data points, and here's a bunch of data points there, data points there, data points there. If there exists a data point to the right of the upper fence, that one, we can consider it unusually high. So this one's an outlier. Or if we find a data point to the left of this, this lower fence, like maybe there's more than one, maybe these two, then they would both be outliers. Good? So the data is less, if a data value is less than the lower fence or greater than the upper fence, it's considered an outlier. Okay, so this guy's an outlier, that guy's an outlier, that guy's an outlier. Outliers. Good. Okay. Looking at our example, we found that Q1 was equal to 28, Q3 was equal to 38. This is before we, I think it was before we tossed in the 100. 28 and, let's go back up here. Yeah, so before we tossed in the 100, we found that the IQR was 10, 38 and 28. Right, so before that, the case where we tossed in that extra value of 100, we had that Q1 was 28, Q3 was 38, so we found that IQR was equal to 10. Right, this is the IQR value, IQR equals 10, subtracting these two, Q sub 3 minus Q sub 1. And then we find that lower fence and we find that upper fence. So the lower fence is going to be equal to Q1, this one is Q1 minus 1.5 times the IQR, and the IQR was 10, that's where that 10 comes from. So that's going to be equal to 13. That's my lower fence. And the upper fence is going to be Q sub 3. That's this value, that's 38. And then the IQR again is 10. So we get to 53. So if we think of it as on a number line, we have this lower fence value over here at 13. And we have this upper fence value over here at 53. And then we have Q1 and Q1 is over here. Actually, I guess I should put it. We have 28 as our Q1 value. We have 38. Right, so this is Q1. This is Q3. This was the upper fence. This is the lower fence. So if we look at our data, coming up here to our original data, right here, here's our original data. Highlight it. Here is all the original data that we were dealing with. None of these scores are below 13, the lower fence, and none of our scores are above 53, which turns out to be our upper fence. So there are no outliers. Right? So there are no outliers here. If a data value is less than the event's considered an outlier. So there are no values less than 13 or greater than 53 in our scores. Therefore, there are no outliers. Let's do the same thing now if we tossed in the extra value of 100. How do we mathematically confirm the 100 is an outlier? So now if we toss in that extra value of 100, that means that these are our results. We already confirmed all those. So let's find our lower and upper fences using this information. So let's do this over here, I guess. No, let me just go over here. Looking at my calculator, including the 100, I can go to Stat, Calculate, One Variable Statistics, L1, Enter. Here are my results. Okay, so let me scoot that over there. That's when we include the 100. So now let's find the things I need. So Q1 is equal to 28. Q3 equals 39. So the I Q R equals Q1 minus Q3, or 39 minus 28 equals 11. Good. That's all we're going to need from our results over here. So let me turn that off, see if my computer can handle that better. So don't need this, so maybe that would help it along as well. As much as I can take off. Okay, so the lower fence is going to be equal to Q1 minus 1.5 times the IQR value. So that'll be equal to 28 minus 1.5 times 11. So that's equal to 28 minus 1.5 times 11 equals to 11.5. 11.5. Lower fence. And then the upper fence, that's equal to Q sub 3 plus 1.5 times the IQR. Good. So that'll be equal to 39 plus 1.5 times 11, which then gives me 1.5 times 11 plus 39 gets me to 55.5. Okay, so that means that any score that's below this value or above this value will be considered outliers. And since this is the case where we tossed in the 100, then 100 is definitely an outlier. Right? So if we kind of think of it on a number line then, here is the number line. Here is that lower fence at 11.5. It's the lower fence. And then let's say over here is the upper fence. Oops. At 55.5. And then in here somewhere is Q1 and Q3. So most of our scores lie in there. If we look at our speeds, there was 20 miles an hour, 24 miles an hour, 40 miles an hour. They were all in there. But there was one, we tossed in one of them that was way over here at 100 miles per hour. So that qualifies as an outlier because it's to the right of the upper fence. All right, that's a good place to finish up or stop with this section. We're almost done with chapter 3, only one section to go.